Welcome back to Tales of Chemistry. Now, let's continue with aldehydes. In the previous episode, we have discussed about nucleophilic addition reactions of aldehydes, and some of those reactions were addition followed by elimination of water. Under that, two of them were already discussed. Addition of hydrogen as well as addition of hydroxylamine. To continue with, the next one is addition of phenyl hydrazine. Now, phenyl hydrazine's structure is a benzene ring, that phenyl group, and NH2. This is phenyl hydrazine. Now, treat this with an aldehyde, RCHO, and this NH2. This H2 is what we are removing. So let us write NH2, NH, and the ring C6H5, phenyl hydrazine. There is elimination of a molecule of water. H2O is eliminated, and there remains RCH, double bond N, NH, C6H5, and the product is called phenyl hydrazone. When phenyl hydrazine is added to an aldehyde or to a ketone, the product obtained is called phenyl hydrazone. Now, let's take a couple of examples. First one, CH3CHO, acetaldehyde or ethanal. Treat this with phenyl hydrazine. There is elimination of a molecule of water. So H2O plus there is CH3CH, double bond N, NH, and C6H5. You can draw the ring also. Now, this will be the corresponding phenyl hydrazone. So, acetaldehyde is the parent's name, acetaldehyde, and then you can add the word phenyl hydrazone, phenyl hydrazone. Okay, now you can repeat this yourself by using benzaldehyde. So complete this reaction, benzaldehyde and phenyl hydrazine. You will be getting benzaldehyde, phenyl hydrazone. Moving on, the next reaction is addition of 2,4 dinitro, 2,4 dinitro phenyl hydrazine, 2,4 dinitro phenyl hydrazine. So what is phenyl hydrazine? NH2, NH, the benzene ring, the phenyl group, and now this is the position number 1. Okay, the darkened one. This is position 1. So this becomes position 2. This is 3. This is 4. I need to mark position 2 and position 4. On these two positions, we have nitro groups. So this is 2,4 dinitro phenyl hydrazine. Now, this is to be treated with an aldehyde, RCHO. Again, removal of water, So this eliminates a molecule of water, and there remains RCH, double bond N, single bond NH, the ring, and on the second as well as fourth position of the ring, there is nitro group. So the name of the product will be 2,4 dinitrophenyl hydrazone. Hydrazine before reaction, hydrazone after reaction. 2,4 dinitrophenyl hydrazone. Okay, we can now repeat this with acetaldehyde as well as with benzaldehyde. So this is acetaldehyde. Treat this with NH2, NH, benzene ring, NO2, NO2. Eliminate a molecule of water from this. So you have CH3, CH, double bond N, NH, and a ring with 2,4 position containing NO2 group. All right. Repeat with C6H5, CHO. Okay. The product will be called 2,4-dinitrophenyl hydrazone. Now, last reaction under this is reaction with semicarbazide. Addition of semicarbazide. Now, what is semicarbazide? Okay, NH2, NH, CO, NH2. All right. NH2, NH, CO, NH2. Now, this is the hydrogen that we will be removing. This is semicarbazide. So let us take an aldehyde, RCHO. Treat this with NH2, NH, C double bond O, NH2. Also note down which is the hydrogen that we are removing. We are not removing that hydrogen of N, which is closer to the carbon. We are removing hydrogen of N, which is away from carbon. Okay, so molecule of water is removed. Then RCH, double bond N, NH, C double bond O, NH2. This is called semi-carbazone. All right. This is semi-carbazone. Now, with this, the addition followed by elimination reactions are over. Okay. Now, one extra note that I want to give here is, this is with regard to the usage of DNP, dinitrophenylhydrazine, because, the 2,4-DNP derivatives are generally orange or yellow color solids. Yeah, so this can be used as a test to identify the presence of aldehydes and ketones. So let us write that down. 2,4 DNP, dinitrophenyl hydrazine derivatives, that is hydrazones. Sorry, derivatives. Okay, they have a color, right? 2,4-DNP derivatives are generally red, yellow, or orange solids. Orange solids. So why are we writing this? We are writing this because of the coloration or because of the formation of dark colored solids, okay, reaction of an aldehyde or a ketone with DNP, 2,4-dinitro phenyl hydrazine, that reaction can be taken as a test to identify the presence of aldehyde or ketone. Okay, now moving on. The next is again very important. So let us mark it very important. This is addition of ammonia. How do aldehydes or ketones? So now let us discuss only aldehyde. How are these aldehydes reacting with ammonia? So if your aldehyde is, say, CH3CHO, all right, treat this with ammonia. Initially, nucleophilic addition takes place, CH3CH and OH. This H is from ammonia and NH2. Okay, so this product here is called acetaldehyde ammonia. This product is acetaldehyde ammonia, but on slight heating, it loses water. So I've written minus H2O, OH from this position, and a H from NH2. So I have put a tick on these two positions just to make you understand. OH and H are eliminated as water, and there is CH3CH double bond NH. Such products are called imines. These products are called imines. Okay, now if you feel adding NH3 and then eliminating water is difficult, what you can do is write it in one step. CH3, CH double bond O plus, okay, H, N, H and H. So ammonia, and just indicate that warming also here. Eliminate a molecule of water straight away. Eliminate a molecule of water, and then you have CH3CH double bond NH, which is the same imine. Okay, so any one of these two ways you can represent the addition of ammonia. Another important point here is ammonia's reaction with formaldehyde. Formaldehyde reacts in a different way. So, formaldehyde and ammonia. This reaction is special. So, this is an example for a polymerization reaction also. 6HCHO formaldehyde combines with ammonia. So 6HCHO plus 4 ammonia gives you CH2 6 times N4. Along with this, we get 6 molecules of water. The product here, CH2 6 times N4, is called urotropin. This is a medicine. This is a medicine used in urinary infection, UTIs. Okay, so this was asked in the last year's board examination. Okay, so mark this as important. Ammonia react with formaldehyde in a different way, and the result is for urotropin. formula of urotropin, CH26N4. Moving on, the next important reaction of aldehydes that we are learning is reduction. Reduction can be carried out using metal and hydrogen like nickel, platinum, palladium, etc. in presence of hydrogen, or you can even use lithium aluminium hydride, LiAlH4. So let's write both of these. Now, RCHO aldehyde. I'm treating this with hydrogen and any one of the metals, nickel, platinum, palladium. Okay, you are adding hydrogen across the double bond. What do I mean by across the double bond? One of these hydrogens will be moving towards carbon and the other one on to oxygen. So you have RCH. Okay, this H will have one of the hydrogens and the other hydrogen will be moving on to oxygen. As a result, we are getting an alcohol. In fact, this can be written as RCH2OH, which represents a primary alcohol. So what is the conclusion? Aldehydes on reduction gives us primary alcohol. So let us write specific examples now. One with ethanol or acetaldehyde, CH3CHO. Treat this with H2 in presence of, let's choose any one metal. Okay, I'm selecting nickel here. H2 will be added across the double bond, giving you CH3C. One H is already there. You will add one H now and one more H on oxygen. So you are getting CH3, CH2OH, which is ethyl alcohol or ethanol. So ethanol is converted. Ethanol is converted to ethanol. Ethanol is converted to ethanol. Again, one more example, C6H5CHO. Okay, treat this with hydrogen. Now, for a change, let me take nascent hydrogens here, meaning I will be using a reducing agent, lithium aluminium hydride. And the product that you get here is C6H5CH and OH, which is nothing but C6H5CH2OH, C6H5CH2OH, which is benzyl alcohol. C6H5CH2OH, that is benzyl alcohol. Okay. Now, the next reaction, again, it is reduction itself, but reduction to hydrocarbon. So let us write aldehydes can be reduced. Aldehydes can be reduced to hydrocarbons. Hydrocarbons. So here we mean directly you are reducing the aldehyde to hydrocarbon without passing through the alcohol stage. So in this first reaction that we need to study, and it is very important, named reaction, Clemenson reduction. Now, in this Clemmensen reduction, you will need aldehyde or even ketone or CHO that is treated with nascent hydrogen. Nascent hydrogen is provided by zinc amalgam, okay, in HCl. Zinc amalgam in HCl is used in Clemmensen reduction. And the product is RCH. You are breaking this double bonded O. Double bond O is broken completely, and out of the 4 hydrogens, 2 of them are used here. The remaining 2 hydrogens are moving away with oxygen in the form of water. All right. So you are getting RCH3, which is a hydrocarbon. So that is Clemmensen reduction. Let us take, say, acetaldehyde here. CH3CH double bond O. Treat this with a zinc amalgam in concentrated HCl. You will be getting CH3 single bond CH3 along with water. So CH3 single bond CH3 is ethane. Therefore, ethanol is converted to ethane directly using a zinc amalgam in concentrated HCl, and this reaction is called Clemmensen reduction, a very important named reaction. One more equally important named reaction is Wolff-Kishner reduction. Here, multiple steps are there. Here also, aldehyde or ketone is converted to the corresponding hydrocarbon directly. So, let's take RCHO, an aldehyde, and treat this with hydrogen. So this reaction is familiar to us. Elimination of a molecule of water takes place. So I'm writing minus H2O, and your product is RCH double bond NH2. Yeah, RCH double bond NH2. Now, this product, that is this is hydrazine, so the product is hydrazone. That hydrazone is then treated or heated with the potassium hydroxide in glycol. Potassium hydroxide in glycol at around 453 to 473 Kelvin. If you cannot remember the temperature, practice writing a delta. So just to show that you are heating, try your best to remember the temperature. Now, here what happens is, in presence of ethylene glycol and potassium hydroxide, you are removing these 2 nitrogens. So one of your products is N2. When you remove these nitrogens, what is remaining there? You have R, C, H, and on the hydrogen, you will again have 2 more hydrogens, that is these 2 hydrogens. So you are getting RCH3 hydrocarbon. Let us try this with CH3CHO. CH3CHO plus hydrogen in the beginning. Show the elimination of a molecule of water. The hydrazone that you get is this. Treat it with potassium hydroxide in presence of glycol at 453 to 473 Kelvin. Remove nitrogen, then you will have CH3, C, H, and the remaining two hydrogens, that is ethane once again. Now, to conclude with these two reductions, whether it is Clemmenschen reduction or it is Wolff-Kishner reduction, both convert aldehyde or ketones to corresponding hydrocarbon. Okay, now if your aldehyde or ketone is sensitive towards an alkali, if your aldehyde is sensitive towards alkali, then we prefer Clemmensen reduction, because in Clemmensen reduction, there is no alkali used. And if your aldehyde or ketone is sensitive towards an acid, then you can use Wolff-Kishner reduction. So both convert aldehydes or ketones to the corresponding hydrocarbon. Depending on the nature of the aldehyde or ketone, you can decide whether you go for Clemmensen reduction or Wolff-Kishner reduction. The next reaction is reaction of aldehydes, reaction of aldehydes with Hi, hydrogen iodide, in red phosphorus. This is also reduction itself. 11th grade also we have studied this. So RCHO, the aldehyde, treat it with Hi. We need excess of Hi. And this happens in presence of red phosphorus at around 423 Kelvin. Then Hi, okay, loses hydrogen to give you I2. Those hydrogens are added across the double bond, meaning you will get R, C, H, break this, and you add two hydrogens on that position. Where will that double bonded oxygen which you have broken, where will that go? That combines with the remaining hydrogens. You have altogether 4 hydrogens, right? 2 of them you have added across the double bond, and 2 of them go away, move away with oxygen. Okay, so this is your balanced equation. So the product here is again an alkane. Let us take one example at least, CH3CHO. CH3CHO with 4Hi in presence of red phosphorus at a high temperature gives you iodine plus water plus CH3CH. You broke the double bonded oxygen. On that position, you are adding hydrogen. So you are getting CH3CH3. That is ethane. CH3CH3. Ethane is the product. Okay. Now, that is all about oxidation of aldehydes. Next reaction regarding aldehyde is oxidation. Oxidation of aldehydes. Aldehydes are very easily oxidized to the corresponding carboxylic acids. So, let's just write it as a statement. Aldehydes are easily oxidized. Okay, aldehydes are easily oxidized to carboxylic acids. Now, what are the oxidizing agents? Oxidizing agents used can be K2Cr2O7 in presence of dilute sulfuric acid. So, dilute acidified potassium dichromate, dilute acidified potassium permanganate, all these can be used as oxidizing agents. Oxidizing agents are those substances which provide us with nascent oxygens. They are providing us with nascent oxygen. That nascent oxygen is used to convert our CHO to RCOOH. RCHO is converted to RCOOH. Okay, now moving on, the next oxidation that we need to study is, it is called Tollens test. This is a test for aldehyde, or this is in general term, this is called the silver mirror test. Tollens test or silver mirror test. So under this, the first step is aldehyde need to be heated. Okay, aldehyde need to be heated with freshly prepared Tollens reagent. Freshly prepared Tollens reagent and heat it with aldehyde. So you will get a silver mirror. If the compound taken is an aldehyde, then a silver mirror can be seen at the sides of the test tube. Now, question number 1, what is Tollens reagent here? Okay, Tollens reagent is ammoniacal, you must study this, ammoniacal silver nitrate solution. So you now know the source of silver mirror, ammoniacal silver nitrate solution. That is called Tollens reagent. Now, when you treat it with an aldehyde, equation is not compulsory to study, RCHO. Okay, treat this with Tollens reagent AgNH3 twice OH. Okay, and heat it slightly in a water bath. And your product is RCOONH4, ammonium salt of carboxylic acid. Now, aldehyde is becoming carboxylic acid. Okay, but since you are using ammoniacal silver nitrate solution, instead of acid, you are getting ammonium salt of carboxylic acid. Along with that, silver is getting precipitated. Silver is, getting collected at the sides of the test tube, and ammonia plus water. So you will get to see that silver coating or silver mirror on the sides of the test tube. Now, if you feel equation is difficult, you can ignore it. You don't have to write this because the question based on this in the board examination is just suggest a test for aldehyde. Okay, so aldehydes on warming with freshly prepared Tollens reagent gives us a silver mirror. Okay, at the or on the walls of the test tube. Only if you're confident of learning the equation, go for it. Now, a similar test is Felling's test. Felling's test. So here, Felling's reagent is to be used. Okay, now what is Felling's reagent or Felling's solution? Felling's solution is of two types. or there are two varieties. Variety as in both need to be added. Felling solution A is nothing but copper sulfate solution. Felling solution B is alkaline sodium potassium tartrate. Now, if we mix and keep A and B together, they both will react together to give us a complex. So, to avoid the formation of the complex or to avoid a reaction between just this fillings A and B, we do not mix and keep them. So, you will take your aldehyde. Okay, you will take your aldehyde RCHO, then in the same order, first fillings A followed by fillings B is added, okay, and it is heated in a water bath. Heat it in a water bath. From this copper sulfate solution, copper ions will react, and from alkaline solution of fillings B, alkaline sodium potassium tartrate, OH minus ions. So all this react on heating to give you the salt of carboxylic acid, okay, and Cu2O, which is the precipitate. So I'll just write PPT here, Cu2O along with water. The Cu2O is a reddish brown precipitate, a reddish brown precipitate. So your observation is aldehydes, when treated with fillings A followed by fillings B and heated, you will get a reddish brown precipitate. Now, this is a very important test because aromatic aldehydes, that is as per our syllabus, the only aromatic aldehyde that we have is benzaldehyde. Benzaldehyde does not give this test, does not respond to this test. So the advantage here or the importance here is, if a question is asked, how do you differentiate between acetaldehyde and benzaldehyde? You can write Felling's test need to be conducted. Acetaldehyde will give you a reddish brown precipitate, whereas no such observation is seen with benzaldehyde. So the question is, suggest a test to distinguish between acetaldehyde and benzaldehyde. Okay, now the next reaction which we are going to learn now is a very important reaction of aldehydes. It is called aldol condensation. Aldol condensation. Okay, so first condition is, okay, we need presence of dilute alkali. Aldol condensation requires dilute sodium hydroxide. Second requirement is the aldehyde or ketone which you are using, which you are taking, must contain alpha hydrogen atoms. So, alpha hydrogen atom or atoms, minimum one alpha hydrogen atom is needed on the aldehyde. So whichever aldehyde you are taking, it must possess alpha hydrogen atom. So let me write here those aldehydes that cannot react. HCHO and C6H5CHO cannot answer this or they won't react. Okay, aldol condensation is not answered by formaldehyde and benzaldehyde because both of them do not contain alpha hydrogen. Okay, now what is this alpha hydrogen? Let me tell you. Consider acetaldehyde, CH3, double bond OH. All right. So this is your functional group carbon. This is your functional group CHO, right? So the carbon adjacent to the functional group, carbon adjacent next to the functional group, that is called the alpha carbon. And the three hydrogens here on alpha carbon, all the three are called alpha hydrogen. So I hope the meaning of alpha hydrogen is clear here. Okay, so let me explain this to you step by step. First of all, you are taking dilute sodium hydroxide, right? So in presence of dilute NaOH, your alpha hydrogen is lost. So you have a H plus and also you have CH2, CHO, and the CH2 here has a minus charge. Now, if at all you are wondering how has this happened, look at this. This is your CH3, C double bond OH. Okay, and from dilute NaOH, OH minus, if you take this hydrogen, okay, one of the alpha hydrogens are lost. So you remove H plus, then you have CH2, CHO, and this bond that remains as a pair of electron on your carbon. Now, so first step in aldol condensation is this. In the second step, take one more aldehyde, same aldehyde, acetaldehyde, one more unit is taken. Treat this with CH2, CHO, but the H plus which you have removed, that is also present. Okay, now this negative charge will be attacking the carbon, carbonyl carbon, negative charge on CH2, that will be attacking the carbonyl carbon, which makes the pair of electron move towards oxygen, and then your hydrogen will be moving on to the same oxygen. So this is step 1, then this is step 2, and step 3, H plus migrates to the oxygen. So you will now get CH3, CH, single bond OH, CH2, CHO. So actually this is aldol, and that is all about aldol condensation. But in most of our reference materials, you will find elimination of a molecule of water, which happens on heating. When you heat the OH, okay, this OH and one of the hydrogens from alpha position, hydrogen, beta position OH. From the beta position, you remove OH. So you are eliminating a molecule of water. Okay, once you eliminate a molecule of water, there is CH3, CH, double bond, CH, CHO. Now, this is alpha, this is beta position. So you are getting alpha beta unsaturated aldehyde. Alpha, beta unsaturated aldehyde. Okay, so you can write the IUPAC name carbon 1, carbon 2, carbon 3, carbon 4. So this is butene al. But for 4 carbons, al for CHO, ene is for the double bond between carbon 2 and 3. So but 2 in second position in. Okay, so that ene's last letter E is to be removed to add the secondary suffix to in, then al. Okay, one al is not needed because al has to be always on the first position. But 2 in al. Okay, fine. Or 2-butanal can also be written. Now, that is about aldol condensation. As I told, aldol is that beta hydroxy aldehyde. Beta hydroxy aldehyde is called aldol. But everywhere you will notice this one extra step also. In the board examination, if the questioners write one example for aldol condensation, you can stop your reaction here. But if they have mentioned aldol condensation followed by heating, then that alpha beta unsaturated aldehyde will be formed. Okay, let us take one more example for aldol condensation. Let's do it with propanal. Propanal is CH3, CH2, CHO. Okay, when you treat this with dilute alkali, from the alpha position, hydrogen is removed. This is the functional group. This is the alpha position. So you will get CH3, CH. Two hydrogens are there, but I removed one. Here a negative charge and CHO plus H plus, that hydrogen which we have removed. Again, treat this with another molecule of propanal. Okay, and I need this carbon to attack the carbonyl carbon. So I'm writing my CH3 like this, CH3, CH, CHO. Now, H plus is also present. What is the first step? Negative charge attacks the carbonyl carbon, double bond shifts towards oxygen, and H plus migrates to the same oxygen. Therefore, you will get CH3, CH2, CH, OH, and here CH, CHO, and this carbon already has a CH3. Suppose if you are heating this, you will eliminate a molecule of water, that is OH from here, and H from the alpha position is removed. And what you will now have is CH3, CH2, okay, CH double bond C, CH3, CHO. This is also alpha beta unsaturated aldehyde. While naming it IUPAC way, 1, 2, 3, 4, 5. 5 carbons are there. So paint. There is a double bond between 2 and 3 position. 2 in, last letter E is removed so as to add the aldehyde. Okay, in and al. In What I missed is the CH3. Where is CH3? On the second position. So 2-methyl pent 2-enal is the name of the compound. So these two examples which we have studied now are examples for aldol condensation. Now, if I use one acetaldehyde and one propionaldehyde, it is called crossed aldol condensation. Okay, crossed aldol is when I mix different aldehydes. Okay, now crossed aldol condensation, generally questions are not asked in the board examination, but point to be noted is there are 4 products that you get in crossed aldol condensation. Okay, so that is all about aldol condensation. We have learned this with mechanism. Okay, thank you for watching this video. Stay tuned for more videos.